He's Santiago Mazuelas. He's a very interesting trajectory in his CV and also in his research topics. He comes from Valladolid. After doing mathematics and telecommunications with a PhD in both, and after went to the MIT and finally worked in Qualcomm Research Technologies before presenting at the Ramon y Cajal last year, I think, no?
Yes, exactly.
So I don't talk more. Thank you.
Thank you for the presentation.
And this talk is about data. And basically, data in general serves to improve decision making. For instance, in blackjack, the data are the cards that we have seen in previous rounds in that table, and players can use that data in order to assess the odds for the next card of the dealer. Then players can decide whether to stand or ask for a new card using this assessment about the next card, and also using their taste about gambling or about winning or losing money. In blackjack, the value of data depends on several factors. For instance, depends on how many cards are used in that table. Some tables use only one deck of cards, some other tables use up to 8 decks of cards. So of course, if we play in a table with 8 decks of cards, the value of data is very small, and then in those tables are much cheaper. The minimum bet in that table is much lower. Other similar factor is what people call deck penetration. So basically that's the frequency with which the dealer shuffles the cards. In some tables, the dealer shuffles the cards just at the end of the deck. In some other tables, the dealer shuffles in the middle or even before that. So that also determines how useful is the data and also the price to play in that table. More generally, for any application, we have data that might be of many kinds, can be signals, measurements, images, internet clicks, sensor readings, and then we have to choose one action. After we choose an action, we face a consequence. And of course, in most cases, just the data and the action don't determine univocally the consequence, because otherwise it would be just a matter of choosing the action with the most preferred consequence. So in general, both data and action have some influence on the consequence, but don't determine the consequence. What happens is that there is another variable, usually known as a state, that together with the action deterministically determines the consequence. So the state can be a message in a localization, in a communication system, a location in a positioning system, can be a scene in a recognition system, can be the user taste, like in a recommendation system in Netflix, or can be, for instance, the status of a power grid. Then what we can do is, once we see the data, we can guess what's the actual state, and then based on that guess, we can choose the action. But similarly as before, the data alone is not enough to determine the state. So better than just guessing what's the most likely state, we can use the data to determine the probabilities of different states. So those probabilities give me richer information than just a guess. Indeed, those probabilities give me as much information as the original data. In the example of the blackjack, if somebody tells me what are the probabilities for the next card in the deck, I don't care anymore about the previous cards. I can just use the probabilities. Those probabilities give me rich information and also enable to do rational decision making. in the sense that I can choose the action with the expected, with the maximum expected utility. If my utility changes later because I become more risk averse, or I like better gambling, or I'm more scared of losing money, I can change the utility and use the same probabilities. Okay, so this probabilistic processing of data is very informative, but it's also more difficult than just obtaining guesses for the state. So we are going to explore 3 different problems. The first problem we are going to explore is a modeling issue. So basically, from an initial distribution of the state, we can use a new data and compute the distribution of the state given the data. But in order to do that, we need to have an accurate model for the relationship between the data and the state. In simple scenarios, we can assume that just the data is the state plus some Gaussian noise. That's the conventional modeling done in many fields. But in complex scenarios, that kind of modeling is too simplistic. A second problem is a computational problem. For instance, we can have a sequence of a state and a sequence of data. The state is changing through a dynamic model, and data is related to a state via a measurement model. So even if we know exactly both dynamic and measurement models, to compute the update for the probability distribution of the state, we might need to solve these kind of expressions. So in general, it's not tractable. We can't compute exactly these kind of integrals and multiplications, even if we know exactly all the models. If the models happen to be linear and Gaussian, we can do this exactly, and that's basically Kalman filtering. But in general, we cannot solve it exactly. The third problem is the problem of scalability. Is what also people know as the curse of dimensionality. So basically what happens is that in practical applications, we might have many different states, and we can have data related to different states at the same time. So in those cases, if we want to have an efficient implementation, we would like to do independently in each processor. We would like to update the probability distribution of each state separately. In order to do that, we need to assume that the different states are independent given previous data. Those kinds of assumptions are the assumptions done in techniques like loopy belief propagation, etc. But in certain cases, this is an oversimplification, and those methods obtain poor performances. Okay, so as I said in this talk, we are going to explore these 3 problems. And I'm going to start with the second problem, the problem about the computational of the distributions. So as I said, we have states, we have data, both in sequence, and we would like to compute the next probability distribution given the previous one and given dynamic and measurement models. Even though in general we can't compute this exactly, this can serve us as a theoretical mapping phi that takes the previous distribution and gives the next distribution. So at least we have a model for it. Then what happens in general cases is that if we start with a tractable distribution at time 0 and we try to do that exact update, in the next step we will find something quite complicated if we are not able to solve this analytically. But in the first time step is not that bad, because in the first time step we could at least compute numerically, we could at least evaluate numerically this function. The problem is that if we try to keep using that optimal recursion, the distribution will be more and more complex. So this is not something we can do in general. So then in practice, each filtering technique is not the ideal filter, but is a different mapping, phi hat, that instead of getting a complex distribution gets a tractable distribution. And that's something that we can compute again and again. So currently, there are many different filtering techniques. I guess most of you are familiar with some of them. So filtering techniques can be like similar to Kalman filters, extended Kalman filters, curvature Kalman filters, and many others. And other types of filters are particle filters. So those techniques are sometimes either inaccurate or too complex. So Kalman-like filters might be inaccurate when a Gaussian distribution is not enough to approximate the complex distribution, and particle filters can be too complex if we need to use many, many particles. In addition to that, there is a lack for a unifying methodology for the design and analysis of filtering techniques, and each technique does something quite different. The main contributions of this work are basically a general framework for filtering that we call belief condensation filtering, that enable us to describe optimality criteria for filtering, and I'm also going to present effective techniques to implement these belief condensation filters with accuracies approaching theoretical bounds and affordable complexities. Okay, so the basic idea is, I also described before, basically we see the filtering technique as a box, as a mapping that takes as input one distribution and provides another distribution as output. Then each specific filtering technique can be seen as a different box that tries to approximate the ideal mapping with the constraint that the inputs and the outputs have to be tractable distributions. Then we can compare different filtering techniques by comparing how similar are those filtering techniques to the ideal filtering technique. And we can define optimality as the filtering technique that is closest to the ideal filtering technique. In order to measure how similar are these mappings, we need basically to choose a discrepancy function that, given a pair of distributions, gives me a number measuring how similar those distributions are. So we can use Kullbaum-Leibler divergence, Kolmogorov-Smirnov distance, L2 distance, any discrepancy function. Then once we have chosen the discrepancy function, there is a very natural way to compare two filtering techniques. Basically, we can use the same input for the two filtering techniques and also in the ideal filtering technique. And then we can check the outputs of the three filtering techniques. If the output of phi hat is closer to phi of g than phi hat prima for any input, then we would say that the filtering technique phi hat is clearly better than phi hat prima. So if the outputs are always closer to what we want, we say that the filtering technique is better, we call it dominates. So this gives us a partial order on filtering techniques. And this partial order also allows us to define the optimality. Basically, we say that a filtering technique is optimal if it dominates any other filtering technique compatible with that filtering technique. With compatible, I mean that in order to compare two filtering techniques, we need that they accept the same type of inputs. So then an optimal filtering technique is just a filtering technique that dominates all the others. Okay, so at this point, there is a very reasonable scheme to do filtering technique. So if we start from a tractable distribution, what we can do is we can do first do the ideal filtering technique. As I mentioned before, the first time is not so bad because if the input is tractable, the output after doing phi is going to be a complicated thing, but at least it's something that we can evaluate point-wise. So the only problem with the output here is that it's not something tractable. So then what we can do is project back that output into a tractable family of distribution. That's the step that we call belief condensation. So we first do the ideal update, and then we do a belief condensation, and after that we will have something tractable. This is just the definition of belief condensation, and then we said that the filter is a belief condensation filter if is the concatenation of the ideal update with a belief condensation. And we have the following result, basically saying that the filtering technique is optimal in the sense I defined before, if and only if is a belief condensation filter. So this is a kind of important result because this says that the belief condensation filter is optimal, and also any filter that is optimal has to be a belief condensation filter. Okay, so now that we are happy with this type of architecture for filtering techniques, we can focus on implementing those filtering techniques. Here, the only step that is tricky is the step of belief condensation, because this other is just given by Bayes' rule, basically. So now I'm going to present algorithms for belief condensation. First, we need to choose the families of tractable distributions, and two quite reasonable choices are mixtures of exponential families and discrete distributions, meaning distributions with finite support points. Those are reasonable because they can approximate very general distributions accurately, and they are also quite tractable. In this figure, I'm showing the approximations of a complex distribution through discrete distribution with 10,000 support points and using a mixture of Gaussians with 55 parameters. Okay, first of all, the case of a mixture of exponential families. So this is the expression of a mixture of exponential families, and in here we use for discrepancy function the Kullbaer-Leibler divergence. Then this result tells us that if we run this recursion for the parameters in the mixture, we will find a distribution that is close to the original complicated one, of course depending on the initial solution. Even more, if the mixture has only one component, this recursion gives the global minimum in just one iteration. And for the specific case, when the exponential family is Gaussian, we have a closed form solution for the covariances in the Gaussian and for the means of the Gaussians. Similar recursion to the expectation maximization algorithm, if you are familiar also with that algorithm. Yes?
So if you have just one Gaussian, is it
Right.
a Kalman filter?
No. No. So the Kalman filters, well, there are many types of Kalman filters, so each Kalman filter does something different. Extended Kalman filter, for instance, linearize the models. So extended Kalman filter changes the problem, basically changes the dynamic and measurement models. Other filters like unscented Kalman filter or curvature Kalman filter does something different, something similar, but still is approximating the steps, the usual steps in Kalman filter. So those are different. I'm going to show a comparison in performance later. Similar, but slightly different. Basically, the main difference is that we do the approximation at the end. We first do phi, and we do the approximation just when it's totally necessary. We do the minimal approximation. Okay. I will also describe comparison with other methods in belief condensation. Okay, so this is the second case now when the families are discrete distributions. In this case, we represent the distributions using the CDF, and we use for discrepancy the Kolmogorov-Smirnov distance, which is the L infinity norm of the CDFs. So first of all, we have this result that says that for any continuous distribution F and discrete distribution G with M support points, the Kolmogorov-Smirnov distance is always greater or equal than 1/2m. So that's valid for any dimension and any pair of distributions. And at least for the one-dimensional case, we can achieve that optimal distance, basically choosing the support points as some percentiles of the continuous distribution. For higher dimensions, this is much harder to get. Okay, so now then related to the question, I'm going to describe relationship with current approaches. So as I said, there are many different types of techniques: extended Kalman filter, unextended Kalman filter, cubic Kalman filter, quadrature Kalman filter, many different particle filters, some other techniques based on variational methods, expectation propagation, etc. One way to classify the filtering techniques is based on the families of distributions used. All Kalman-like approaches use one Gaussian distribution. Particle filters use discrete distributions. They call the support points particles. And some other methods use distributions that we can factorize or single exponential families. Among those methods, several of them can be thought of as belief condensation filters. For instance, particle filters can be thought of as belief condensation filters in which the belief condensation step is done by random sampling. So random sampling basically approximates the complex distribution with a discrete distribution in which the support points are just random samples extracted from the continuous distribution. Those random samples have obtained a Kolmogorov-Smirnov distance of the order of 1 over the square root of m, which is a suboptimal rate of distance, but at least random sampling is something that can be done for any dimensions. And other techniques, like based on variational methods, can be thought as belief condensation filters with Kalman, with Kullback-Leibler minimization as belief condensation. Kalman filter methods are not directly belief condensation methods. Some changes the models as extended Kalman filters, and these others approximate the original recursions in Kalman filters. So it's slightly different. Okay, now I'm going to show a performance comparison of different techniques for one case study of navigation in harsh environments. Here, the state is formed by position, velocity, acceleration, orientation, derivative of orientation of an agent. Can be, for instance, a car, where we want to know the orientation, velocity, everything. The data that we have in this case study are GPS measurements, measurements from accelerometers, and measurements from gyroscopes. So this can be like a smartphone, have both accelerometers, gyroscopes, and GPS. In this case, dynamic model can be assumed to be linear and Gaussian, but the measurement model is highly nonlinear and non-Gaussian if we are in indoor environments, for example. Okay, in this figure, I'm showing a comparison. In the left is one instantiation. Black curve is the ground truth movement. And in the right, I'm showing the comparison in terms of root mean square error together with the Kramer-Rao lower bound. So we can see that the belief condensation filters with 3 Gaussians obtain accuracies similar to particle filters with, in this case, 60,000 and 30,000 particles. Regarding to your question, in this figure I'm showing the performance of extended Kalman filter and unextended Kalman filter in green. And if you see this purple curve is the belief condensation with 1 Gaussian. So these 3 methods use the same families of distributions, but the approach is slightly different, and we get a better performance in this scenario. I'm not saying that the difference is going to be that big always, but in this scenario with strong non-linearities and non-Gaussianalities, we get better performance. For instance, if you think of it, neither unextended Kalman filter or extended Kalman filter can deal with non-Gaussian errors. It's just a matter of covariances and means, so the type of errors play no role in those methods. Okay, and also in terms of complexity, the belief condensation filters require much less parameters compared with particle filters, and also in terms of processing time, they are much faster. For instance, if we use just one Gaussian, it's very, very fast because in just one iteration of the algorithm, we find the global optimal. Okay, so now I'm going to describe the other two difficulties of this probabilistic approach using, as example, network localization and navigation. So first, just a brief summary of this type of networks. Most of us, we are familiar already with GPS systems, so it's similar. So in these networks, we have possibly many nodes. Some nodes have known location, like GPS satellites, and the rest of the nodes have unknown location. What is maybe different compared to GPS system is that we allow different agents to obtain distance among themselves. So for instance, I can measure the distance with respect to you, and you can measure the distance with respect to somebody else, etc. Then from all the data, from all these measurements, we want to infer the positions of all the nodes. And the challenges here are limited infrastructure, like we might have few anchors. And maybe more importantly, in indoor environments, the relationship between the measurements and the states might be complicated because we might have obstacles, etc. Okay, so for the problem of scalability. In this type of networks, this problem is also known as the whispering in the hall problem. So here what happened is that if I measure the distance with two neighbors, but these two neighbors are also communicating between themselves, but I'm not aware if they have communicated or not, I can't properly use their information because their information might be correlated. So this happens anytime we have a loop in the network. And these loops can be small loops, like just direct neighbors communicating between themselves, or might be the two neighbors are not communicating, but they are communicating with somebody else, and then at the end, we have a long loop. So why this information coupling is hurting localization system can be seen in a very simple scenario. So imagine just two agents. The agent in the left has some knowledge about both x and y coordinate, and the agent in the right has some knowledge about the y coordinate but has no idea about his x coordinate. So in this scenario, it's clear that no matter how many times they measure their distance, the agent in the left is never going to get any information about the x coordinate because the other agent has no idea about that. So in this case, they communicate, they measure the distance, and then the agent in the right gets some information from the agent in the left, and then they can meet like 1 hour later. They see each other, they communicate, they measure the distance, and then the agent in the left will think that he is getting some information about the x coordinate, but this is wrong. This is just because they have communicated in the past and they don't remember. Okay, so then this agent would be over-optimistic about his position, and if he shares that information with other nodes, then all the nodes in the network have wrong estimates. Okay, so most current approaches are based on loopy belief propagation, and they just discard those correlations among the agents' positions, and they might lead to poor accuracies. This figure I'm showing the performance of the optimal algorithm that is centralized, and in green I'm showing the performance of a distributed loopy belief propagation. So in the first steps, the accuracy is good. So this is a network with 100 nodes. In the first step, the accuracy is quite good, but after some time, the accuracies are rather poor. In red, I'm showing the performance of the algorithm that is doing exactly the same as the blue algorithm, but discarding the correlations among the agents. So that's showing that the problem here is the information coupling. Some distributed algorithms account for information coupling but use heuristic methods that might be inefficient. For instance, some methods keep track of who communicated with who and when, and then they keep a very long table with all the communications, share that table with everybody. So those are very, very complicated. The main contributions of this work is characterization of information coupling in terms of Fisher information, and we have determined the intensity of information coupling in different scenarios and outlined the design guidelines based on the theoretical results. Okay, first just a recap of Fisher information. Fisher information provides an accuracy bound for any unbiased estimator. In this case, the estimator would try to estimate the positional states of all the nodes in the network. So then we have that the mean square error matrix of this very long estimator is always bigger or equal in terms of positive definite matrices with respect to the inverse of the Fisher information. In the case of network navigation, the structure of Fisher information matrix is quite interesting. So that matrix is the sum of many terms. The first one is a diagonal block matrix where each block diagonal is related to each agent. And then for each pair of communication, for each pair of nodes that exchange information, we have a term, non-diagonal, with negative terms in the non-diagonal. So the structure of the Fisher information matrix gives me a graph structure. Basically, we can say that two positional states are neighbors if their pairwise information is non-zero. As I said, this Fisher information matrix can be very long matrix. We might have thousands and thousands of agents, and in general, we are interested on just one or few agents. So instead of using the full Fisher information matrix, we characterize what is called equivalent Fisher information. Basically, it's the sure complement of the Fisher information matrix corresponding to that component. Then we have this result. So if we focus in one positional state, we can partition all the other positional states in connected components, in this case 3 connected components. Then we can show that the information obtained by that positional state is the sum of the information obtained from each component. And then the information obtained in each component is the information from neighbors minus this term here that accounts for the uncertainty of the neighbors and also for the correlation among neighbors in the same component. So this is the complicated term. For the special case in which each connected component has only one neighbor, we call these neighbors isolated, and then in that case everything is easy. We can do distributedly, we can get information from one neighbor and then from another neighbor, then from another neighbor, because the information is the sum of the information for each neighbor. So this is the simple case that can be done distributedly. And the information from each neighbor accounts only for the uncertainty of that specific neighbor through this term that we call effective information. In general, the neighbors are not isolated, and we want to determine the information coupling in those cases. So what we can do is we can select a subset of links, and if we remove those links in the Fisher information matrix, we obtain a different Fisher information we call reduced Fisher information, and a different effective link information from neighbors. Then a separating set would be a set of links such that after removal we obtain isolated neighbors. we have this result that says that for any separating set, the actual equivalent feature information is upper bounded by the pairwise information from neighbors and lower bounded by the sum of the effective information from neighbors after removal of the separating set. So the operational meaning of this result is that if we are able to discard some information links, we can transform a situation where we have information coupling into a situation without information coupling, into a situation in which we can distributedly obtain the position of the agent. Now we can define precisely what is information coupling. Information coupling induced by a separating set is just the difference in information between the actual equivalent information and the effective information from neighbors. If the neighbors are isolated, this term is 0. If they are not isolated, this term is positive definite. In general, it's quite complicated, the expression of this term, but in networks with just one separating set, with the separating set is just one link, we can find an expression from which to extract insights. So for instance, we can say that the information coupling depends basically on 3 terms: the pairwise information in the separating set, the uncertainty of the separating set, and this term here that depends on the information from neighbors and on the correlation between the neighbor and the separating set. We can also prove that when the pairwise information in the separating set increases, the information coupling increases. If the uncertainty of the separating set decreases, information coupling increases. And if the correlation between the neighbor and the separating set decreases to 0, then the information coupling also goes to 0. So these are some insights interesting for design. And maybe a more important result is that this information coupling decays with the hopping distance in the network, with the network distance. So basically, if we have a network with just one loop, we can prove that the information coupling for this positional state related to this separating set decreases exponentially with the network distance, with the hopping distance. So the operational meaning of this result is basically that the information coupling can be safely discarded as long as the separating set is several hops away from the positional state. We can prove this exponential decrease in this simple network, but we have observed this behavior in general networks by simulations. So these are networks with 100 and 200 nodes, and we can see exponential decay of the information coupling. Notice that the y-axis is logarithmic scale here. Okay. Finally, the last topic is about the modeling of data in complex scenarios. So that was the problem, how to have an accurate model for the data and the state. One case in which is quite clear that the relationship between data and state is highly complicated is in localization in indoor environments. So here in this figure I'm showing an indoor environment and nodes that are taking wireless measurements. We have 2 cases. One case is a long line of sight scenario, and the other case is non-line of sight scenario. So the difference is also kind of intuitive. In the line of sight scenario, the direct path is very strong, so we can very accurately estimate the distance between the 2 nodes. While in the non-line of sight scenario, the direct path has to go through the wall and then is much weaker. So in this case, it's much harder to estimate the distance. And also intuitively, all the signal can give us some information, because the shape of the signal can also give us information about the obstacle or how many obstacles the signal are going through. Okay, so the current approaches focus on estimating the distance. So from the data, they try to estimate the distance between pairs of nodes. Some techniques estimate try to detect if the situation is line of sight or non-line of sight, and then subtract some bias in non-line of sight situation. However, in general, data is not enough to be able to disambiguate the distance. So the main contributions of this work is a new paradigm that instead of focusing on estimating the distance, focus on estimating a function of the distance. Instead of estimating just one number for the distance, we estimate a function of the distance that is higher for distances that we think are more likely. This function of the distance offers richer information, and the estimation of this soft range information can be achieved using unsupervised machine learning techniques. Okay, so this is basically what I was saying. We use the data to get a function of the distance. We call soft range information. This function of the distance is any function that is proportional to the conditional of y given d. So first I'm going to show in a very simple example why this soft information is much more informative than just a distance estimate. So in this very simple scenario, the data has only two numbers. One number is a distance value, and the other number is just the output of a line of sight or non-line of sight detector. The detector can have errors, and that's why the distance estimate sometimes is inaccurate. So in this very simple scenario, we have three anchors and one agent at the origin. Anchor 1 and anchor 2 are in line of sight, so we can very accurately determine the distance to that anchors, and we know that the agent is in the intersection of these two blue circles. However, the third anchor is in non-line of sight, and in this case, the detector detects erroneously as a line of sight case, so that we put a much higher likelihood into a highly inaccurate distance. So any method based on distance estimate will use just this number here and will result in a very inaccurate position when we merge the information from the three anchors. However, if we keep all the function, even if we keep this small bump for the actual distance, after merging the information with the other anchors, we will find the accurate position of the agent. So this is in one instantiation. This figure in the left, I'm showing the results in many repetitions and changing the probability of error in the detector. So if the detector is very reliable, both distance estimates and soft range based obtain the optimal Cramer-Erlauer bound. But if the detector is not reliable, distance estimated based are highly inaccurate, while soft information is still very close to the Cramer-Erlauer bound. Okay, so this is just one toy example to show the benefits. Now I'm going to show how to get this soft information in practice. So in practice, getting the soft information is basically equivalent to estimating the joint distribution of the data and the distance. If there is no prior knowledge, just the joint is a soft range information. If there is prior knowledge, we can just divide by the prior knowledge. So then the problem that we face can be casted as a joint density estimation problem. So we can estimate that joint using machine learning with the two stages. In the first stage, in the offline stage, We can perform a measurement campaign in one or several indoor scenarios. We can obtain many pairs of data and distances. Then from those pairs, we would like to estimate the joint distributions of data and distance. And the main problem might be that the data can be highly dimensional. Like if we want to use all the signal, we might have like 1,000 dimensions. So first, we do a dimensionality reduction step, and then we estimate the joint distribution of the data with reduced dimensionality. This is the offline stage, and then so this can be, both steps can be enabled by unsupervised machine learning techniques. Then in the online stage, every time we get the new data from two nodes, we can do the dimensionality reduction of that data sample, and then we can just plug in that data sample into the stored joint distribution. If we plug that data into the joint, we will get a slice of the joint distribution that would be a function of the distance. Then we can use that function of the distance as a soft range information for localization. Okay, now just to finish performance assessment of these methods, we compare the performance with respect to conventional approaches based on distance estimates, methods based on least squares, and methods based on supervised machine learning, like support vector machines or Gaussian processes. Dimensionality reduction, we use several methods like principal component analysis, Laplacian eigenmaps, and also physical features. Physical features is the conventional approach, is based on using features like power of the signal, delay of the signal, rise time of the signal, etc. And for density estimation, we use kernel density estimation or the empirical risk minimization. So we observe that methods based on soft range information outperform methods based on supervised machine learning and distance estimates, and obtain performances similar to the performance obtained in line-of-sight cases. More specifically, we observed the improvement around 50% with respect to methods based on least squares, and around 30% in methods based on supervised machine learning. For instance, we observed that in 90% of the cases, we get errors smaller than 1 meter, even if most of the measurements are non-line of sight. Okay, so just to finalize some conclusions, the probabilistic processing of data can obtain richer information, can be used for rational decision making, but the probabilistic processing faces several difficulties. Those challenges also offer opportunities for research. I have presented a new methodology for filtering called belief condensation filtering, techniques for high dimensional cases and information coupling, and a new paradigm for localization in harsh environments called soft range information. And so that's basically it. In those references, you can find more details about the techniques presented. So that's basically it from my side. If you have questions or...
Thank you very much.
Sure.
I have just a curiosity.
Sure.
You can go back 4 slides, please. Which is the different? Yeah, this one. The different types of the.
Yeah, I didn't specify
yeah,
here.
I think that is.
Right. So, yes. So basically for dimensionality reduction, we have 3 methods and 2 methods for density estimation. So basically, these 6 types are the 6 combinations of the 3 things. So I remember, so type 1 is using physical features and empirical risk minimization. Type 2, I believe, is principal component analysis, and these others are kernel density and so on.
But there are no strong differences.
They are, so the main difference is like in terms of complexity, the methods based on kernel density estimation are more complicated. Yeah. So then in the next slide, I focus on type 1 and type 2 because the others are similar but more complicated. Yes.
I have a question.
Sure.
Because in data science, the main focus of the people is we need more and more data.
Right.
And your work,
Right.
the size of your data sets,
Yeah.
big and small.
Currently, I'm in a small data regime still because I feel that there are still many challenges even with small data sets. There are many things that we need to learn how to do. So for me, even going with images is like a little bit too much, or going to gigabytes or terabytes for me is a little bit too much at this point. I want first to understand better how to solve it for small data sets before going to big data. Hopefully, the techniques for small data sets are also useful for large data sets. Yeah, but yeah, that's my point of view. Yeah.
Okay. Questions? No? Thank you very much for your.
Sure. Thank you.
Muy bien.
Would the
Yeah.
slides be or the references, the last slide of your publications, are you gonna make it available or
I
can we catch your email and you write it on the board or?
I can, yes, I can make it available. Yeah, I think it's, I mean, few of them are still under revision, but I think it should be totally fine. I have some other conferences with some preliminary work that are already in internet. I can send you a list. Yeah, I can maybe send you an email with a list of references. Yes, I can send it to. Yes, you can share those links with the people. Yeah, sure.
Okay, thank you.